Example 3 says find the partial fraction decomposition of this. And the difference between this problem and what we saw yesterday is we have a quadratic factor that's not factorable. X squared plus 7 is a binomial. It's a sum. If you consider 7 is the square root of 7 squared, it's the sum of two squares. It's not got to be a difference of squares to be factorable, so we can't use the technique that we did yesterday. We just put letter over factor. So that's one difference here. So what I want to do to set this up then is I got 3x plus 16 over my factored form, which is x minus 2 times x squared plus 7. I'm going to set that equal to a over x plus 2. So that was just like normal. Or sorry, x minus 2. I don't want plus 2. This factor is a linear factor just like yesterday, so we get a single object a over the factor x minus 2. But for the second factor, which is x squared plus 7, since it's a quadratic factor on the bottom, we have to put a linear factor on top. So we have to account for both an x to the first power and a constant that are possible on top of that one. If we had, like, let's say x cubed was down here. Let's say we had x cubed on the bottom. Then we would have to put well, first of all, you'd have a over x, b over x squared, and c over x cubed. That's what you do on that one. So never mind on that one. So it's got to be some binomial or something to a power or thing that, but maybe x to the fourth plus 7, something like that. That wouldn't factor either. So ax cubed plus bx squared plus cx plus d. So you have to account for whatever this power is. You got to go one less power on top. Is what I'm trying to get at. Now, one thing I want to show you today is called the Heaviside cover-up method, and I wanted to wait till today so you do yesterday's homework using the techniques from yesterday so that you have that under control, because you have to use yesterday's technique most of the time. But there are places where you can use the cover-up method. Everything we did yesterday could have used it, and if I showed you yesterday, everybody would have done it that way and they wouldn't have practiced the skill. But here's what I'm going to look at here. This is a problem from yesterday, example 1. The way the cover-up method works is this. If I want to find out what a equals, I look at what's underneath a, which is x minus 5, and I ask myself the question, what makes x minus 5 equal to 0? And what's the answer? 5, right? 5 minus 5 is 0. Then let's just use a little color here. I'm going to cover up that factor over here in the problem. That's why it's called the cover-up method. You're covering up. So I'm trying to figure out what a equals, and I figure out that x minus 5 makes x minus 5 equal to 0. I cover up x minus 5 over here in the original problem, and a is going to equal 5 plus 11 over 5 plus 3, which is 2. All right? And then we do the same thing for b. What makes x plus 3 equal to 0? Negative 3. We cover up x plus 3, and we replace x with negative 3, and then b is going to equal negative 3 plus 11, which is 8. Negative 3 minus 5 is negative 8. 8 over negative 8 is negative 1. There's a and b figured out. And again, I don't want to show you that way yesterday, because then everybody's going to use that way to do it, instead of going through this whole process here, which can't be avoided at times. In this case, I can use the cover-up method on this, but I can't use it on this. It only works when you have a linear factor in the denominator. So if I go ahead and use the cover-up method here, what makes x minus 2 equal to 0? 2. So then I come over here and cover up x minus 2. And then a is going to equal, again, replacing x with 2, 3 times 2 is 6 plus 16, over 2 squared is 4 plus 7. That's 22 over 11, which equals 2. All right? Once you've used the cover-up method to get your answer, you still need to have the entire thing here. You're covering it up while you get that answer. And once you find an answer, you can change the letter that's there into what it actually is. So you create your structure, you do what you normally do, but then again you can find any linear factor, anything that makes that equal to 0, cover that thing up, replace that number for x, and that's what a is going to equal. It's called the Heaviside cover-up method because the mathematician who came up with it was called Oliver Heaviside. That was his name. It's an unfortunate name, that's what his name was. Oliver Heaviside. It's an E at the end. I think back in the old days, like Old English, they usually came up with last names based on your job, your profession, your physical appearance. So I'm guessing Mr. Heaviside might have been heavy in the side, maybe busting out on the side, maybe. Anyway, but that's kind of how it happens. Anyway, once you figure out what a is equal to, now we're simply going to do what we did yesterday, which is the common denominator is x minus 2 times x squared plus 7. So I do x minus 2 times x squared plus 7. I still have to figure out what b and c equal. There's no cover-up method for nonlinear factors, so I can't do anything about that. And that gets me to, if I multiply it all through, I'm going to get 3x plus 16 on the left equals. When I do 2 over x minus 2 times x minus 2 times x squared plus 7, the x minus 2's cancel, leave me with 2 times x squared plus 7. And when I multiply b plus c over x squared plus 7 times x minus 2 times x squared plus 7, the x squared plus 7's cancel, leave me with bx plus c times x minus 2. So I create the same similar structure as we did yesterday, right? And then I can keep going on. This is 3x plus 16 equals, this will be 2x squared plus 14 plus, and I got to FOIL this, it'll be bx squared minus 2bx inside product plus cx, last and last negative 2c. And then it's a matter of matching up the powers to the powers in order to establish the values of b and c. And what I'm noticing is I've got 2x squared, and I've got bx squared plus bx squared. I've got no x squareds over here, right? So officially what I have is 0x squared. So I know that 2 plus b has to equal 0. So I can figure out very easily that b is equal to negative 2. So sometimes you don't have to get a system of equations, you can just find things as you go along. B equals negative 2 is pretty simple there. If I keep looking for things that match up, 14 is a constant, negative 2c is a constant. Unless it has an x on it, it's going to represent a constant. And the two constants should add up to the constant. If I take a look at those, I'm going to get 14 minus 2c is equal to 16. If I move the 2c to the right and the 16 to the left, 14 minus 16 is negative 2. Positive 2c ends up over here, so c is equal to negative 1. And I found everything I need to find, right? I got one more relationship that these two are x terms, right? So negative 2b plus c should equal positive 3. But we've already found b and c, so it's not necessary to really do that, right? So if you're able to find what you're looking for without going through all the steps, that's fine. This right here was kind of unnecessary. I'm just going to erase it. So finally, once I know what a equals and b equals and c equals, now I'm ready to go. So I'm going to write the decompositions 2 over x minus 2. Now there's two ways to handle the bx plus c. b is negative, c is negative, right? So I can go, here's one of two ways. I can put a minus sign here, and then 2x plus 1 up here. Remember, there's minus in front of the fraction. It's minusing both things, so minus 2x and minus 1. That's one option for it. The other option for it would be to keep this as a plus, and both of these are negative. Minus 2x, minus 1. Take your pick how you want to write it. I personally like the first one better. I think, I like that one better. I think it's a little bit more elegant in how it's written, but they're both correct. So take your pick how you want to write it, and I'll take either answer.